Okay, so topic 6, random variables and discrete probability distributions. Keller's chapter 7, the one in Seward's chapter 6. So this is the table of contents. Random variables, we will first talk about random variables, what it is, and discrete probability distributions, mean and variance of discrete random variables. Maybe we will go over up to here, and then next, the rest of the topic 6 will be covered during the online lecture. Bivariate distribution and typical distributions such as binary distribution and Poisson distribution. Okay. Random variable. Actually, random variable is very interesting thing. Okay. Random variable, namely, is a variable. But if you look at the definition, then the definition, it says random variable is a function or a rule that assigns a number, a number, to each outcome of an experiment. Okay? For example, if you toss a coin, and there is a head, 앞면, and tail, 뒷면, right? And you assign number 1 to head, and number 0 to tail. And we use this capital letter Y, capital alphabet Y, to denote random variable. So Y is equals to 1. If in the sample space you have an outcome head, then we assign 1. If we have a tail, then we assign 0. Okay? We have to distinguish this with the event. Event was what? Event was a set. But now we assign number to an outcome, not an event. Okay? So, for example, we may draw 2 dice. Okay? Then the sample space may be 1, 1, 1, 2, 1, 3, 6, 6. And a random variable is a rule or function that assigns a number to an outcome in the sample space. So sample space, we have these kind of guys. Pair of 2 numbers, right? You draw 2 dice, right? Then maybe we can define random variable x, which is the number on the first die. Okay, we can assign any number. We can define any random variable. This random variable I define x is the number on the first die. So if you give, for example, like 1 and 4, then x should give us 5. Right? And x can take 6 values. 1, 2, 3, 4, 5, 6. Right? Let's define another random variable y. Y is the number on the second die. Okay? So y can also take 6 values. 1, 2, 3, 4, 5, 6. Right? They are random variables. Then why we introduce random variable? In the previous topic, we introduce events, and we assign probability to an event. Like for example, like A is an event. Let's just say, let me write down like this. A is the sum of or whatever. First die is greater than 3. Okay, that's the event. Maybe we define B, the sum of 2 die. The sum is greater than 5. The sum is greater than 5. We can define many different events, and we assign probability to these events. Probability A, probability B, and then how many events we can define with these 2 dice? There are bunch of events we can define. But we have only limited number of alphabets, A, B, C, D, E, F, G, and we may not have any common sense about which alphabet for which event. Right? Some people may define A for the sum of the die greater than 5, but some people say A is different event. So in that sense, we introduced a random variable, and we use this random variable to assign some probabilities. Okay. For example, like this event, instead of saying probability of A, we can say this is a probability of X. The number on the first die is greater than 3. This looks much more mathematical, right? Instead of probability A, probability of X is greater than 3. This is actually more convenient. Then in terms of X, we can define many different events. X is less than 2, X is 6, whatever. Okay. And for the second event, this sum is greater than 5, then we can use probability of X plus Y is greater than 5. Okay. With X and Y, these two random variables, we can define many different events in terms of their mathematical operations. Okay. That's why we introduced this random variable. Okay. So that is actually the reason we introduced random variable. Now, from now on, we will almost never use event. We will just start with a random variable. Okay. Always we will try to introduce, we will define a random variable, and we will write down probability in terms of that random variable's values. Okay, that's what we are going to do. Okay, so let's move on. So we use these uppercase letters, the alphabet, to denote random variables. X, capital Y, capital Z, capital W, whatever. And its lowercase counterpart, small x, small y, small z, represent the value of random variable. Okay. So, for example, in the previous case, x is y, maybe y. Y is 1 and 0, head, tail, and this guy's small y. Okay. Maybe a little bit confused. Okay, what's the difference between capital Y and small y? Capital Y is still variable. It can be realized any numbers that the random variable can take. But small y is a particular value that is already realized. But we don't want to write down it as a 1 or 0. It's a generic value. Let me repeat this in Korean. Maybe in English it's maybe hard to understand. Maybe in Korean, even in Korean it's hard to understand. But this small y, let me repeat this in Korean. Please excuse me. 왜 캐피탈 Y, 대문자 Y랑 스몰 Y를 썼냐? 대문자 Y는 여전히 랜덤 베리어블입니다. 얘는 어떤 값이든 리얼라이즈 될 수가 있어요. 익스페리먼트가 일어나면은 이 값이 리얼라이즈 될 겁니다. 익스페리먼트가 일어났죠? 그럼 리얼라이즈가 됐을 겁니다. 뭐 0이나 1이 생겼겠죠. 그럼 그걸 0이나 1로 쓰고 싶지 않기 때문에 그게 0일 수도 있고 1일 수도 있는데 걔가 그냥 모음 값을 갖는다 그런 어떤 펑셔널 폼을 만들어주기 위해서 이 스몰 Y를 쓴 겁니다. Okay? 그래서 okay, so we can, for example, we can write down probability of y equals to 1, probability of y equals to 0, right? And this may be 0.5, if you have a fair coin, 0.5. But I want to write down this more generically. Then this is probability of capital Y is small y. Okay. In general. Okay. That's why we use this small y. Okay, and here it shows this probability of capital X is small x is basically probability that the random variable is equal to small x. Are you guys following me? Questions? Okay, let's move on. There are two types of random variables. First one is discrete random variable. Second, continuous random variable. Discrete random variable is like in the previous examples. You toss a coin, head or tail, 1 or 0. Only two things. You can count how many things there, how many values this random variable can take. Then that is discrete random variable. Continuous random variable, for example, you go to a street and you ask a person's income. That income can be any number between 0 to infinity. Okay? We cannot count how many numbers the random variable can take. Then that is basically continuous random variable. Okay? So countable, then discrete, basically not countable, then continuous random variable. And in this topic, we will talk about discrete random variables. Only in the next topic, we will talk about continuous random variable. And next thing is probability distribution. Once we introduce this random variable can take some values, right? Especially discrete random variable, we know how many, values it can take. We can count them, right? Then each value, there is a probability, right? Probability of x equals 0, probability of x equals 1, probability of x equals 2, We know these probabilities, and this probability, we can write down this probability as a table, or you can write down this, you can draw the graph of these probabilities, and that is basically probability distribution. Okay, so probability distribution is nothing but just a table, formula, or graph that describes the value of a random variable and the probability associated with those values. Okay, so basically probability distribution is the probability associated with those values that the random variable can take. Okay, for example, you toss a coin, then the small x that capital X can take two values, 1 or 0. 1 is head, 0 is tail. Then probability of capital X is small x is 0.5, 0.5. That is just the probability distribution. That's just simple. Okay. If you roll a die, then x is 1, 2, 6. Probability of x equals to small x is 1, 6, 1, 6, 1, 6. That is probability distribution. Okay. As the random variable have two types, discrete and continuous. Also, probability distribution has two types, discrete and continuous. This is basically discrete probability distributions. They are discrete probability distributions. Okay, and in the next topic we will talk about continuous random variable and continuous probability distributions. So these discrete probability distributions have two interesting properties. First property is naturally this probability must be between 0 and 1. That's for sure, right? Probability is always between 0 and 1. Okay, probability of x equals to 1, probability of head, which is 0.5, between 0 and 1, probability of tail must be between 0 and 1. And if you add up those probabilities associated with these values that x can take, then this adding up those probability, you have to have 1. Right? Probability of head plus probability of tail must be 1. Right? So that is two features, two properties of the probability distribution. Okay. Example: when we roll a die, 주사위, we can say a random variable yi is the number of a die in the ice trial. So often statisticians or mathematicians use this notation as y of subscript I. Why? Because sometimes you want to run or experiment many different times. Like you toss a coin like 10 times. You draw a die like 10 times or n times. So y1, first toss of a coin, y2, second toss of a coin, y3, third toss of a coin, and nth toss of a coin. And sometimes some people may be interested in the sum of these tosses. Okay, because of these kind of reason, we introduce this subscript notation, which make our life easier, hopefully. Of course, if we don't have to learn this class, we don't have to introduce this, but given that conditional on that we have to learn this course, introducing this kind of notation makes our life easier. Anyway, this random variable yi has a discrete probability distribution with the probability of yi equals to small y, where the small y can be one of those 6 numbers because it's a 주사위, right? 주사위. Like this, right? One of those 6 numbers. 1, 2, 3, 4, 5, 6. If the die is a fair die, then probability of yi equals to small y is 1 over 6 for any value of y. Again, you can see why we introduce this small y. After we introduce small y, writing down the probability distribution becomes much easier. Otherwise, we have to write down all those 6 numbers. This is going to be our probability distribution. But if we introduce small y, we can just write down like this. Right? Probability of yi is y is 1 over 6 for all y. In the previous session, I didn't introduce this equation. 수학 in math, people often introduce this notation. The reversed y, reverse a. This is for all. Let me repeat this in Korean. 한국말로 한번 할까요? 수학과 대학원 같은 데 가면 경제학과에서 많이 써요. 그래서 미시경제 같은 데 많이 써요. A를 거꾸로 뒤집어 놓은 거는 for all이라는 뜻입니다. 수학에서 많이 쓰는 노테이션. Okay, anyway, so this is an example of a probability distribution, discrete probability distribution. Every number is between 0 and 1, and if you add up those 6 numbers, it's going to be 1, right? So that is the probability distribution. Okay. Second example, in the United States, they do some kind of census survey, and they have this statistical abstract, which is published annually and based on census. And there are many different kind of features about the population of the United States. And one of the questions asks household to report the number of persons in their family. Okay. And the next page, the table summarizes the data. So there are 116 million households in the United States. I don't know which year it was, but 160 million household, and there are number here. These numbers are basically the number of family members in each household, right? So here X is the number of family members in a household. Right? Number of family members in a household. And that X can take many values actually, many natural numbers like 1, 2. Some household may have like 100 people. But for simplicity, we just categorized 7 or more into just one category, right? Okay, so 1, 2, 3, 4, 5, 6, 7. And then in the second column, it shows the number of households in each category, right? So there are 31,001,000 households are basically a single person household, and 38.6 million households are 2-person household. 18.8 million households have 3 family members, okay, and so on. Okay, so these are the small x, and we can using this information we can assign probability. So probability of x equals to 1 is there are 31.1 million households among 116 million households. Probability of x equals 2 is 38.6 divided by 116, and probability x equals 1.4. X equals 7 is 1.4 divided by 116, and this number is 0.268 and 0.333. So, and these are basically the probability distribution. Okay, that's probability distribution. And if you sum them up, that the sum will be 1. Okay, this probability will be 1. Simple example of discrete probability distribution. Again, there are a countable number of values that the random variable can take, and there are associated probabilities. Next. And actually this example is about the United States population. Okay? Usually we don't know the population. I mentioned in the topic 1 or topic 2, I mentioned that population is usually unknown. But in the census, basically they ask all those people in the population. So it's a special case we know the population. Once we know the population, then in the population there is a feature of population which we call parameter, right? Population parameter, such as population mean, population variance. So we can calculate the population mean and population variance in this special case. And next slide, we have the formula for the population mean. Okay. In topic 3, we talked about the population mean. The population mean was mu. And mu in topic 3, we write down mean as a summation I equals 1 to capital N xi divided by n, right? Capital N. So basically it means what? We add up all those values in the population and divide by the number of observations in the population. That was the population mean. But then in this topic, suddenly we say population mean is the weighted average of all of its values. But there is no concept of the weight. No concept of weight here in topic 3, right? This was topic 3. Let's go back to the example to think about this. Here, let's think about this at 7. 1, 2, 3, 4, 5, 6, 7. How can we calculate the population mean number of family members? Let's think about that. Then how you will calculate this? If I use the topic 3 method, then how I will calculate the mean is this. I have to add up all possible numbers and divide by the number of observations. Then I have to add up ones. 1, 1, 1. How many ones? There are 31.1 million ones. So I have to add up these 31.1 million ones. And then how many twos? There are 38.6 million twos. I have to add up sevens, 1.4 million. And then I will divide this by 116 million. Right? Then I will get the mean value of the family size. Right? And nobody will do this. Right? This is stupid, right? Then how you will do this? If you are average, if you have average IQ, then we will do this right with this 1. How many ones there? There are 31.1 million ones. Okay, plus 2 times 38.6 million twos. da 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 plus 7 times 1.4 million ones, and then we add up this and divide by 116. Okay, you will never count 1 plus 1 plus 1 plus. That is stupid, right? That's how we calculate the mean. Okay, let me slightly rewrite this and put this 116 to here. Like this. Then 1 times this 1 is small x, right? And this guy is probability of x is x. Okay. 1 and probability of x is 1. 2 times probability of x is 2. 7 times probability of x is 7. So this formula is summation. Maybe I will put it here. Summation all x times probability of x equals to small x. Basically, these guys are the weights. These guys are weights. Weight is basically how frequent, right? How frequent that each number that capital X can takes is gonna be the weight, and you multiply that weight on the value that capital X can takes, and you add up. Then that is the weighted average, and that is the population mean. Okay. So population mean is x times probability of capital X is x, the associated probability, and you add up these numbers for all possible value of x. Okay, that is the population mean. Okay, that is this formula here. Population mean is summation or x times probability of capital X equal to x, which is mu, and we have another notation for this, which is expectation of x. Okay, expectation of x, or expected value of x, or expectation of x. Okay. This is population mean, usually unknown, but in the very special case, in the census data, we can calculate this population mean. But here, one thing that I want to emphasize is this formula. Expectation of x is summation or x probability capital X is small x. So here what I want to emphasize is this guy and this guy. Basically, what we have, taken the weighted average is x. Okay. Here is x. So if you look at this part, this is basically expectation part. Expectation part is basically the weighted part and taking the sum. What we have done is we take weighted this x based on its associated probability. If this guy is x squared, or x probability of x equals to small x, then this is gonna be expectation of x squared. If you take a weighted average of x squared, then that is the expectation of x squared. Okay. And another thing that I want to emphasize is this and that. Pink is capital. expectation is for random value. And when you calculate, this formula has a value that the capital X takes. Okay? I'm very picky about this notation. So in the midterm exam or in the final exam, I ask you to calculate, for example, expectation of X, but some of you may write down expectation of X. Then I will ask 조교 선생님, teaching assistant, to take off at least 1 point. This is wrong. Expectation is for random variable. Okay? And this is the value. This is just gonna be X. X is the value. Right? This can be just a number. Number's expectation is just number, which we will see in a few slides. And this is not this. Okay? Only the random variable can be weighted averaged. Okay? Every year I mention this to the student. I'm picky about those notations. Capital X, small x, estimator and estimate, those kind of things. Then students learn how to deal with this kind of problem. So they write down something like this. They write down X, small x in that way. So 소문자 and 대문자 구별을 못하게 하려고 이렇게 쓰는 학생들이 있는데, later, once you learn statistics very well, lot of statistics, then later we will not distinguish those capital X and small x, because we know when that thing is a random variable and when that thing is the value. But at this point of time, we are still in the nascent stage of learning statistics. So that's why I try to let you make sure to distinguish the random variable and its realized value. Okay? Let me repeat this in Korean. 한국말로 한번 하겠습니다. 저 알파벳 대문자로 된 확률 변수 랜덤 베리어블하고 소문자로 된 그 숫자 값 랜덤 베리어블이 테이크하는 그 값, 그 구분을 꼭 하셔야 됩니다. 그 값을 expectation에 넣으면은 그 값 자체는 랜덤네스가 없기 때문에 그냥 x로 빠져나오게 됩니다. Okay. Let's try to calculate the population mean in the previous example in the table, this table. Actually, I already write down the formula here, right? This is basically mu, which is summation x times probability of capital X is small x. So this value is what? This value is 2.52, something like this. 2.513. So maybe let me write down this. 2.513. This is how we calculate the expectation of x. So expectation of x is summation x. It's 2.513. This looks very easy, but I'm sure that I and your friend ChatGPT or Gemini can make very complicated question that you may face some difficulties to apply this very easy formula. Okay? Very simple formula, but in some situation it could be quite confusing. So have to be careful about what's the random variable, what's the value, what are the values that the random variable can take, and what are the associated probabilities. Okay, so variance. Now the variance. Population variance is calculated similarly. It is the weighted average of the squared difference from the mean. So x, when we write down sigma square in the topic 3, it was 1 over n, summation I equals 1 to n. This is population variance. So x minus mu xi minus mu square, right? the value that the x can take minus mean, you take a square and you sum them up and divide by n. Now in the same logic as the population mean, we use x minus mu square here, but we weighted this based on the value that x can take. Okay. So, and then we sum them up for all possible values. This is because we have a discrete random variable. Random variable can take only, like say, two values. Okay, then we don't have to, we don't have to worry about how many observations there. There are only two values possible, 1 and 0. Then we only need to know how many ones and how many zeros out of the total number of observations, right? So that is because we have discrete random variable, so that's why we can do this summation for all x. Okay, and if you look at this formula of the variance, again here we have this, right? This is what? Weighted sum, right? Weighted average part. That is what? Expectation, right? So this guy is expectation of x minus mu square. No, because x is not the random variable. X minus mu square. Okay. So variance is actually the expectation of the square difference between the values that x can take minus the mean. Right? It's the square difference between the value that x can take and the population mean. And standard deviation, population standard deviation is the square root of the variance, which we already learned. Okay. How to calculate the population variance from the previous example in table for the family members table. Go back to this table. There are 7 values that x can take, and there are probabilities here, right? So we use this, then variance of x, which is first value that x can take is 1, right? Minus mean. Mean was calculated previously, 2.51 square times the probability. This one is summation. Like this, right? This you can look at this, right? Look at this formula, right? And probability of x is 1 plus 2 minus 2.51 square. Probability x is 2 plus 3 minus 2.551 square. Probability x is 3 plus plus 7 minus 2.51 square. Probability x is 7. And we plug in those numbers, the probability 30.31.1 divided by 116 plus 2 minus 2.51 square, 38.6 divided by 116 plus 7 minus 2.51 square, 1.4, 116. Then we can calculate this variance, which is close to 1.958. Okay. This is how we calculate the variance. Very tedious calculation. I just want to let you know how this formula is indeed, practically implemented. Okay. Questions so far? 괜찮나요? 여기까지? I hope maybe you guys have learned this previously, but it's okay even if you haven't. Laws of expected values. Those expectation and variance have laws. So first law is the laws of expected values. In order to introduce the laws of expected values, we introduce the random variable x and the c, small c, which is a constant. So constant is what? Just the 상수. It's a number. The constant is a number. A number. Number. It's not a variable. So c is, for example, like just think about c as a 5, say. Okay? Just number. Expectation of c, the constant, is just the constant itself. Expectation of 5 is 5 because it is always 5. Okay? And then second thing, we can pull the constant out of this expectation. Expectation is a linear operator. So if you have a constant is added to the expectation, added to the random variable, then that expectation becomes expectation of x plus c. Expectation of x minus c is expectation of x minus c. Okay. And you multiply constant to the random variable and you take expectation, then you take expectation first and then multiply by c. We can prove this expectation of cx is summation of all x, c times x, probability x equals to small x. By definition, as I mentioned earlier, expectation is this, right? This is a e part, right? And inside we have this cx, and c can be taken out from the summation. Very simple proof. Very simple proof. Right? It may be interesting to ask this kind of question during the midterm, right? Very simple proof. Lastly, I want to go over the laws of variance. Okay, laws of variance. Laws of variance. Variance of a constant. Constant is just a number. Variance is namely how this thing is varying, right? Based on your random experiment. Okay, but constant does not vary. It doesn't depend on what kind of random experiment you do. So variance of constant is 0. Okay, variance of constant is 0. You can also prove this by yourself. The variance of a random variable plus a constant is just the variance of the random variable. So variance, the constant does not basically contribute to the variance if the constant is added to the random variable. Okay, so variance of the constant plus random variable is just the variance of the random variable. You can also prove this. Maybe you can use this all x plus c minus mu plus c square probability x equal to x. This is the variance of x plus c, right? Because expectation of x plus c is expectation of x plus c, right? The variance of a random variable times constant. So variance of cx is c square variance of x. Okay. This easiest way to prove this is expectation of cx minus c mu square. Why? If you let y is cx, then expectation of y is c, expectation of x, which is c mu, and then you can calculate the variance of y, which is expectation of y minus expectation of y square, which is gonna be this. Variance of y is expectation of y minus expectation of y, quantity square, and you take expectation of that. Then you have this, which is expectation of c x minus mu square, right? That is gonna be expectation of c square x minus mu square, and c is gonna be taken out from the expectation, right? Because this is constant. So this is this. Okay. There are many different ways to prove this. I just choose the most simplest way in this session. In the previous session, actually, I used more complicated way, but that is both very simple, both very tedious, but you can easily prove this. You can also use this formula to prove this. Okay, the definition of the variance. Okay, but the important thing is if we multiply constant to the random variable, then variance is actually multiplied by the constant square. Okay, that is the this formula provide us. Okay. Any questions before we finish? Okay, let's finish here, and happy Chuseok, and I will see you guys in 2 weeks.